You just send the number.
Okay, so here we
Hey,
go.
you have a piece of Sorry. It's true. Financial aid is icky.
Oh, yeah.
I don't know where to put my dead dad to get income from.
Nice.
Well,
They still get.
Okay.
He's not working
So-
very hard.
So let's talk about where you're at. So hopefully, I think everybody got done with the first 2 trials yesterday.
Yeah.
So again, you have to look at when you do these calculations of rate. So the whole idea on this, because of the fact that iodine has a very distinctive color, like we couldn't do this lab with like an acid-base neutralization because everything like sodium hydroxide and hydrochloric acid, oh, how long does it take? Well, I don't know, it just goes clear. Cool. So that's the advantage of this reaction, is that there's 2 main things. One, the reaction takes a while. Okay, it happens, but it kind of goes slow. So that iodine, like I think some of you had like about 5 minutes yesterday for that first reaction. Part of that is because it's so cold in that room. My apologies right now, Bethany, it's going to be cold in the room. Okay, so if you're already cold, you're just going to shiver. My apologies, light a Bunsen burner. I don't care. So just don't light anything on fire. That's all. Okay, so you can sit there and go. Okay, so. Don't set Jaden on fire, that's how I am.
Whatever.
I said not
I
to.
don't care about the rest of us.
Yeah, no, this is very
Well,
good.
but I said
We're all
Jaden probably
expendable.
close, so that was my concern. So,
Yeah.
anyway, back to the
Let's
story.
find out the calorie drum temperature.
So, what you're gonna do is you're gonna base this reaction on, in this case, the rate of disappearance of the iodine. So like on that first one, you're gonna know the initial concentration of the iodine, which should be, if you do the math, 0.0010. So that's the initial concentration of the iodine, okay? Well, obviously, when you get done, what's the final concentration of the iodine? 0. Okay, mine is 0. And let's say it took like 5 minutes, so that's gonna be, you're gonna divide that by like 300 seconds, okay? That's how you're gonna get the rate. What you should see, hopefully, is that the other times, especially on reaction 2, hopefully that time was about half of what the first reaction was, okay? Ish, okay? So today you're gonna do reactions 3 and 4. So here's gonna be the whole point of this. When you look at the bottom of page 4, and this is like a formal lab write-up, okay? Means you write out everything. And when I wrote this, I kind of said, okay, we're gonna go through this step by step by step. So how we're gonna determine that rate, there's gonna be some value of x times the concentration of the acetone raised to the x times your I2 concentration raised to the y, and your hydronium ion concentration raised to the z, okay? So we have 3 different possible reactants that could determine the rate or influence the rate of this reaction. So on rate 2, here's what I want. Where it says rate 2, you're gonna go in and you're gonna write K, you're gonna put in the value for the acetone at that on reaction 2, which is gonna be 1.60, and then you've got 0.0010, and that's gonna be to the X, and that's gonna be to the Y, and then you're gonna have 0.20 to the Z. And then you're gonna do the same thing for rate 1. You're gonna put in the same values, X, Y, and Z. Then on the bottom of page 4, you're gonna take reaction 2, and you're gonna divide that by reaction 1. Now, in an ideal world, your values would work out to be perfectly whole numbers, okay? And it would be really nice, and for the most part, this lab works, okay? You just might have to get a little bit creative on the rounding, just saying. So when you get done, when you get X, Y, and Z, 2 of them should be first order, and 1 of them should be 0 order, okay? So, like I said, you might, because it's so temperature dependent, you might have to get a little, let's just call it roundy, okay?
Round.
Little round, which
Little
I
round
know is a
shorty.
horribly non-scientific term, but we might have to get a little roundy. Just go with it. Now, here's the whole point. And if you're not sure if you're right, ask me and I will tell you. Because there's no point, you cannot do parts 2 and 3 of this lab if your orders of magnitude are wrong, okay? So when you get done in the middle of page 5, where you're gonna write that rate law, so you're gonna have R is gonna equal K times something, okay? When you get done, if you're not sure if that's right, ask me and I will tell you. Because if that's wrong, parts 2 and 3 are just gonna be train wrecks, okay? So assuming that that part is right, would you two quit? It's like watching a metronome, or stop, okay?
That's not.
That's weird because you're both in sequence, okay? God. Oh.
I'm not moving anymore, it's just Charles.
Okay, so now here's the whole point of this. For the 4 reactions, and I want you to pay attention to what I emphasized when I wrote this out. On the middle of page 5, you're going to find the rate constant K for all 4 reactions. And in big bold letters, I tell you, show me the calculations down below. For all 4 of them, okay? For all 4 of them, I want to see how you got the value of K, and you want to pay attention to the fact that they had the same units. So you're going to go through and you're going to calculate K. Typically, your K value is around 10 to the negative 5th, okay? It's an ish. Hopefully there's something around there. If you have K values of 10 to the 4th, you have done something horribly wrong, okay? Typically, your K values are very small. So you're going to calculate the 4 K values. Then you're going to find the average. You do not have to show me how you calculated the average. I know you all can add 4 numbers together and divide by 4. That's not what I want to see. What I want to see is the 4 individual calculations of K. So you're going to add those together, divide by 4, boom, you're going to get an average. Hopefully something times 10 to the negative 5th. Now, this now becomes the predictive part of the lab. The next thing you're going to do is that you are going to pick for a different combination from what you have of iodine, the hydrochloric acid, and the acetone. And you're going to come in and water. You're going to have all 4 of them. And all of those volumes, just like the other ones, have to add up to 50 milliliters. So here's the big picture. You're going to say, okay, maybe I'm going to have 0.05 molar iodine or whatever, okay? You're going to add these together, whatever those molarities work out to be. And then you're going to plug those values back into the rate function that you know. So at that point, you will know your average value of K. You're going to know what the concentrations are. Based upon those concentrations, which are different from any of the previous 4, and they cannot be 0, they all have to be non-zero values, you're going to say, okay, based upon this, this should be my rate, okay? So over here, so down here at the bottom of page 5, you're going to write down, hey, here's the volume. 20, 20, 5, 5, 5, 5, 20, 20. I don't care. Just make the volumes add up to 50, okay? Then you're going to calculate the concentration of the acetone, the iodine, and the hydronium ions after they have mixed, just like you've done before, okay? Then, on the top of page 6, this is where you are going to show me your rate calculation, because everybody's values of K are going to be different. Everybody's concentrations are going to be different. I have no answer key. The only thing I can grade you on is the fact that, hey, did you show me this work? Okay? Now, at that point, you're going to have your rate. Now, you also know that the rate equals the change in concentration of your iodine, over time. Cool. Here's the predictive part of the lab. You're gonna calculate your rate based upon the concentrations of your iodine, hydronium ions, and your acetate. You're gonna calculate the rate. You're gonna know what this number is. You're gonna know the initial concentration of your iodine. Boom, you have that number. Solve for time. Based upon this, you're gonna say, I predict that under these conditions, this reaction should take 145 seconds, whatever you get, okay? Now, what's gonna be important is that you are going to come over to me and you're gonna say, hey, salt and solubility, sign off on this, okay? Because I don't want you to like run the reaction and then go, oh, I predicted 146 seconds. It took 145. No, okay? The idea is that you predict the time. So you're gonna, and so help me, you show me these calculations. Because if you come up and you show me 6 and I do this,
Run.
that's bad. Run. Okay? Run. And you better hope that your rate of running is faster than my rate of running, which wouldn't take much. But because if I can't see what you have done, okay, I can't begin to tell you how bad things are going to happen. All right? Okay?
That's exciting.
I'm just telling you in advance. Okay? I'm just telling you in
Warning.
advance. Because it's not that difficult a computation, for the love of God. You're taking rate and you're solving for time. You're taking the concentration and you're dividing it by rate. You're not doing calculus, okay? Right? You're not doing the chain rule or anything weird like that. It's simple algebra. Just show me the steps.
I took a test today. I would kill it.
That's what we need to get done today. Okay? So, find the overall order, run the 2 reactions. Find the order of the reactions, find your value of K, predict what's going to happen. Ready to break.
And then put this on the back.
Oh, you'll know I'm out.
No, that's, we're off on that.
No,
Kevin, did you stop the camera?
he's our